Hello, everyone. We will go ahead and get started with our webinar for this month. And thanks again for everybody giving your time to Sudarshan in there. So I am recording this as I always do. And so all of those in attendance will get the recording link as well as the PDF of the presentation. If you have any questions along the way, feel free just to put them in the chat box there and I'll address them all at the end of the presentation in there. So with that, we will go ahead and get started with the presentation. And today we are talking about the impact of finishing on application performance. So we've done this topic a couple of times over the years. I refreshed it so that I'm taking a little bit of a different perspective and looking at the types of finishing that are done and how they result in different performance aspects of it. So we'll go into what is actually pigment finishing, and why the finishing is critical beyond just the chemistry of the pigment. And then I will provide you with a number of examples to show you how that finishing can impact the end performance. So why does finishing matter? As I mentioned, it's a combination of both the chemistry of the pigment, but also the formulators who develop pigments. They engineer that pigment to do a specific job, basically, in its end application. So the finishing links the process to the performance. So that includes, and by no means this is an exhaustive list, but primarily includes color strength, transparency or opacity, how well it disperses, and then stability of that particular pigment in the final formulation in here. So when our R&D teams are given the task to develop a certain pigment, they know the application where it's going to, they know their options, and they know the impact of the different options in finishing, what they do and how they transform the pigment once it's been synthesized in there. So they are always going to select the options available to them that are best suited for that particular pigment product, as it was intended for the ultimate destination for where it was developed for. It's not to say that it's not going to work in other areas, but the primary development goals are you always targeted at a end application. So we've seen this slide many times, but it's always important to revisit it and really sink in the information that it does contain. Simple slide, but it has a lot of information there. That's very important to you as a formulator to select to use when you're selecting a pigment. So the bulk of the performance properties, somewhere around 75%. Plus minus, that really does come from the actual chemistry of the pigment in there. This is why we have classes like the high performance pigments and the classical azo pigments. They deem a certain level of performance aspect purely by the chemistry of that particular pigment. The remaining performance really does come from that finishing. And by finishing, we kind of bring together both the mechanical aspect of it as well as the chemical aspect of it. Mechanical, as the name implies, is we're really impacting the particle size and the hardness of that particular pigment. And then the chemical aspect of it will help in that dispersibility area. So, this is a very generic process flow diagram for the creation of the synthesis of an organic pigment. In here, I just wanted to highlight the areas where finishing takes place. On the mechanical side, these are all after the filter press, after the um, the pigment has been synthesized, and the bulk water removed. So there's some amount of drying that's done from directly from the filter press, and then there's always some amount of milling classification that's done as well. From the chemical side, these happen in two different places. One, the primary one is really right after the pigment is synthesized. The crystals are formed, where different surface treatments or additives can be used to coat, if you will, the pigments themselves for the end application that it can be done. Then at the very end, where the individual batches of pigment are blended to the final lot, that's another opportunity where additional chemical finishing can be done for that particular product. So I talked about the application. That's where our R&D teams focus their efforts when they're developing a pigment. So if a team is developing a pigment specifically for plastics, they know the types of things that they need to dial into that particular development so that it is as easy to disperse in a plastics scenario as it can be. Plastics have a very short residence time, and that energy into the dispersion is not as great in there. So we need to be able to make those pigments to be as soft as possible, as small as possible, and also that particle size being as narrow as possible as well. I know they do try to have no or very minimal additives in the surface or on the surface, primarily because we don't want to interfere with that dispersion properties. Again, trying to get to that ultimate dispersion in the application and process. For pigments that are for coatings and inks, there's a lot more flexibility in the end dispersion process, as well as sub-applications. There's water, there's solvent, there's UV. There's a lot of formulation types that have to be considered in there. So the interesting thing is, if you ever looked at a full brochure line card of pigments, and you compared the number of pigment choices from a plastics perspective versus a coatings or inks, you'll see the amount of the number of product offerings is always going to be greater in coatings and inks because there's so many sub applications in those areas, as I just mentioned before. So there's a lot of specific finishing choices used to match to that sub application. An example. So this is an example of three varieties of pigment blue 15-3. Each of these were developed for a specific application area. And some of the information that you can glean from the TDS will key you into those properties. Specific gravity is one area that can tell you essentially how much additional surface treatment is done. So for example, if you look at the coatings grade pigment, that specific gravity is higher than the other two, signifying that there's probably additional additives that are there for that coating end formulation aspect of it. Mentioned on the plastic side, particle size is key. So this one, you can see that it is the lowest of the three in terms of particle size, because we want to be able to provide a pigment that is the best that it can be for that dispersion property. Other aspects, for example, on the ink side, that one is the lowest in terms of the oil absorption, which signifies that there is there's not as much surface treatment on there, and the pigment itself doesn't absorb as much of the polymer as you would potentially see in other areas. So these are some of the clues that you can take away from reviewing the properties that are on the TDSs that you receive, and how you can relate that information to your application in there. It's not a holy grail. It is just there to guide you in your selection process. So finishing, we talked earlier about the types of finishing. Mechanical, definitely there for particle size and size distribution control. Its main impact is on the dispersion itself, as well as the strength that you can get out of the particular pigment. Surface treatment or chemical, different ways depending on the end application and the actual chemistry of the pigment. Inorganic coatings typically are in the silica, alumina types of surface treatments that are done for inorganic pigments, whereas organic typically tend to be polymeric in nature, surfactants or other dispersants that are placed on the pigment themselves, with the goal of matching it up to the formulation. So that's where hydrophilic, hydrophobic comes into play. To be able to match up the dispersion and formulation with the pigment itself. There are other more advanced types of treatments, polymer coating and resin treatments. Here is an example. Weather-treated mica effect pigments fall into this category. Our chrome-free weather treatment is a polymeric in nature. Anti-corrosive activation, these are another area where more advanced types of treatments are done for the purpose of the properties that it puts out there. So if we dive a little bit deeper into the actual finishing choices that our R&D teams have when they're developing a pigment, on the mechanical side, I mentioned, excuse me, I mentioned that the drying and the milling are the two key choices that they have. Just some examples of the types that are available in the production facilities that they use when they select the process. So obviously the objective is to remove any water or solvent. Usually it's just water by that time. But the important thing is to preserve that performance of the pigment. And in this case, why it matters is probably of the techniques that we use here, this is probably one of the more important choices that we make, because we really need to control that agglomeration of the pigment. So when the pigment is synthesized, that's where the primary particle comes in, and that's the last time you ever see a primary particle. They automatically come together as the aggregates. And then when you take it out of the bag, that's where the agglomerates are coming in there. So the best bet is to be able to get down to that aggregate size in here. So your choice of drying is directly impacting how much agglomeration that we get in that one. Particle size distribution definitely impacts that one. And it sets it up for the next step, any kind of milling that is done for that one. More importantly, depending on the chemistry, each of those chemistries will create a crystal, and that crystal will have a structure. So we really do need to make sure, depending on the chemistry, that we preserve that structure in there. So for example, if the chemistry results in a needle-like structure, we certainly do not want to break those needles into smaller needles in there to be able, then that will ultimately impact the final properties of that one. And then, of course, it does also result in how well the pigment will get dispersed in the end formulation in here. So all of these are on paper, they're just ticks off on a sheet, but they are key in terms of how we choose the process technology that's available to and match it to the end use for that particular one. So, you know, as I say here, drying is just not the moisture removal. It defines that downstream processability. And again, it goes back to that comment I made that drying is probably one of the most important parts of the finishing that we have to take into account. So this chart really just gives you a feel for a few types of drying techniques that are used in making a pigment and how they factor into their as far as how they influence different parts of the property and the process. Agglomeration, moisture control, crystal integrity we talked about, throughput and cost efficiency. They kind of go hand in hand with the cost of the actual pigment itself in here. But everything has to be to match up in here. So this gives you a feel for the types of drying that are available and how they impact these types of properties. As I mentioned, the agglomeration control impacts the dispersibility. Moisture certainly is a processing stability part in here. And then, of course, as I mentioned earlier, crystal integrity is directly related to the color performance. If we're breaking the crystals by a very aggressive drying process, then we shift the color from away from its intended position. So, all this taken into consideration, the drying step, it really does set the foundation for not only the success of the milling in the pigment manufacturing process, but also your milling and dispersion success as well. An example. So this is an example of a pigment blue 15-2, an alpha CPC blue. And in this case, we are comparing two different drying processes that on the same product itself. And here we are evaluating it in a solvent-based polyurethane type formulation, and in both the color of the tint tone process as well as the strength, we see a difference between the end result purely by the choice of the drying process that we use. From a color perspective, this is an alpha blue, so we want to be able to develop the most red shade in there because it's an alpha one, so it's always going to be red shade. So we see here that the drying process number 2 does provide the best color development in there. And then from the strength perspective, it tells us that we're developing a smaller particle size and maybe even a more narrow distribution of that particular pigment. So these are some relevant examples on how the choice of drying process impacts the end result. The next phase is milling technologies, and there's a lot of variety of milling technologies in use in making pigments, and they're all chosen for a very specific reason, just like the drying is. Ball mills, although not so much as a powder, but ball mills are actually used in pigment manufacturing for the beta blues, the 15-3s and the 15-4s, where we take the crude and we run it through a ball mill to get the particle size of the crude to a small level before it moves on in the process to become the final pigment. Jet mills and air classification ones, those are key ones that are widely used in our production facilities. They have their purposes in there. So, for example, jet mills. One of the key things that that brings to the finishing techniques is it's a very there's no contamination from grinding media or collisions with the the shell itself. These are good for very high purity types of applications. So think inkjet pigments that need a high purity type of a scenario for those the inkjet heads in there. Heat sensitive pigments, these operate at a much lower uh, overall temperature. So we're not going to introduce high heat where the color of the pigment itself can change with a high heat operation. Air classification mills, these are actually two types of processes in one, where the particle size is reduced as well as those big and small tails can be removed from the system so that the particle size distribution is much more controlled in here. So these types of systems are also used where the more the high tech type applications come into play. So obviously for the objective is really to control that particle size and the distribution ultimately, because as a pigment we want to make sure that the end user, you as a formulator, can achieve the absolute best strength that you can, and the absolute best dispersion that you can with that one. So the milling choice does directly impact that one. So as I mentioned a little bit with a previous slide, heat sensitivity is one thing to be able to include in the selection. So for a good example is the classical pigments that tend to be the azo type of pigments where they have much lower heat sensitivities than the high performance in here. So they might not be, this might be a better choice for a milling technology for those high, that more sensitive to temperature. Particle size, depending on the end application. Again, the higher the application, the more important particle size and distribution tends to be. Contamination, we talked about, for example, the inkjet performance there is where that jet mill would be the preferred choice for the product. Also, from a production perspective, we always have to go through that throughput and control balance, just as you have to balance all of your properties and outputs. We too have to balance our throughput and the control and quality that we input into each of those. So each of these have to be matched towards that particular product. And then, as I mentioned at the very beginning, the actual end use. Is it going to go for coatings, plastics, or inks? That all will dictate how much, or what the specifics as far as a dispersion would be required. So that helps us to choose the choice of milling. Some examples in here. So particle size results in surface area. And so that's always going to result in how you formulate in here. So this chart is a series of pigment yellow 83 pigments that are differ in particle size in there. So as a result, they result in a different surface area. So using the standard starting point from a formulation perspective, the surface area divided by 4 will give you a clue as to where to start on how much dispersion to use in your formulation. So the more opaque the pigment is, the smaller the surface area, the less dispersion that you're going to need. The opposite is true for the more transparent one. It's going to generate a lot of surface area, so you're going to need much more dispersion than you would in a comparative opaque grade. The other interesting to note here, with the new Sudarshan having three very unique entities as part of the new Sudarshan, the top three pigments are, or top four pigments are considered opaque grades. One from the legacy Sudarshan, one from the legacy Hoibach, and a couple from the legacy colorants part of it. So you can see a variety of surface areas in this category of opaque pigment yellow 83s. What that signifies is that each entity has their own unique choices of finishing that they impart on these particular products, which then ultimately results in slightly different surface areas in there. So these are all of the things that come into play. So when we help you to make recommendations for certain products with a portfolio that's as large as Sudarshan's is now, there are many more options to consider to best fit your formulation. So if we now move over to the chemical portion of finishing choices, we have a number of examples that can display that one. So in a powder coating formulation, here those same three pigment blue 15-3s that we looked at the very beginning of the presentation. Here we're looking at those same ones and how it translates into the L value or strength in this powder coating formulation. So the same three products that we saw earlier, the coatings and the plastic grades, they result in a very similar strength value in there. So they disperse similarly in this formulation. But the ink grade does not disperse as well and results in a higher L value or less or less strength in there. And from the earlier TDS data that we looked at, it does show that it is the lowest in the oil absorption and the lowest in the surface area. So some clues there that give us why it doesn't interact as well as the other two in this formulation. Effect pigments. They fall into the same category as organic pigments, inorganic pigments, because their finishing technique on the chemical side is in the treatment or choice of treatment, whether we do it or we don't do it. And then if we do apply a surface treatment to it, we have choices of how much and what chemistry to use when we treat the pigment. So why we use surface treatments for pearlescent pigments? A number of reasons, and we're ultimately trying to either slow or prevent an undesirable reaction in the final formulation and application area. And primarily these are due to the TiO2 containing pigments, because TiO2 is a highly photodegrading chemistry in there. In water-based formulations, there can be some humidity effects of the formulation, and we try to slow that process down. They can also be used to help with rheology of the system, or the overall performance with respect to durability. And then there could be areas where we're just doing additional inhibition of undesirable effects in there. So there's a lot of ways we can use surface treatments on mica pigments to get to where we need to be from the end application area. Example, we've used this one before, But here we're looking at two things. We are looking at the choice of the chemistry of the surface treatment and how much we put on the surface of that particular product. We are looking at the uh, gloss retention of this formulation. The mica itself is the finest one in there. So these tend to be a lot of surface area to cover. So the sparkle is going to be small. You can get a feel for that particular pigment in the upper right-hand corner. The data is from the ultra accelerated weathering that we've done, which is about 1 month is about equivalent to 1 year in Florida. And so we can see that there's definitely a chemistry difference. The green is the chrome-free surface treatment chemistry, while the red lines are the chrome-containing. And then the thickness of the line dictates how much of the chemistry is added onto the particle itself. The thicker the line, the more the more surface treatment is used in here. So ultimately, to get the best gloss retention, the chrome-containing weather treatment is the desired chemistry of in here. And with this very small particle size, we're going to need the highest amount of surface treatment to be able to retain that gloss in this formulation. So performance drivers. There are a number of areas to consider when selecting a pigment. And these 4 areas are key in doing those. So I have some examples in each of these areas. So from a dispersion and processability, you're going to have a poor dispersion if you can't wet well the pigment in the dispersion. Certainly, once we disperse it, it has to be stable. So we want to be able to create a very stable dispersion, of course, and that also carries through to the finished product, the end product, especially if it gets mixed with other things. We want to be able to maintain that stability all the way through to the end use. Ease of incorporation. From the stability perspective, flocculation, again, that goes back to that agglomeration resistance. Rheology, always want to make sure that we're getting the most out of it. Typically, rheology is definitely related to how much strength we can do, and how much energy that you're putting in actually gets transformed into the dispersion development. Storage stability is key. On its own, the dispersions on their own, as well as when they're mixed with other dispersions in other final formulations. We want to make sure that everything stays stable. Certainly, as I mentioned, wetting and grinding and stabilizations, these are the key steps in creating a dispersion. And this is really true, it doesn't really matter what the application area, everything you see here is included in all application areas, just a little different in terms of how it gets there and the processes used to get there. But ultimately, when you take the pigment out of the bag on receipt, these are going to be bigger clumps. They're loose, but they're bigger in here. And ultimately, the dispersion process, you want to be able to get to that finest aggregate size, not primary size, aggregate size. And then once you get there, you want them to stay that way in there. So you want a good, stable dispersion. So wetting, really wetting is just removing those micro air bubbles that are trapped within those agglomerates in here. And we want to replace those bubbles with the resin of choice, the solvent of choice, to be able to help break those apart. So I have a little bit of a video here that that you can get off of the BIC website in here, so that it gives a very good visual of pigment wetting and why it's important. So this is a phthalo blue in a water system. So as you're putting it in, It really just sits there and looks back at you. There's no wetting in here. And so if you introduce something like this to your grinding process, you are going to have some troubles. But the use of an additive for helping wetting or dispersant, you can start to see how easily it goes down. So your best quality premix is going to make your dispersion process that much more efficient. Once you've dispersed it, you certainly need to make sure that it is stable. Again, another video from Bic to show flocculation, what makes a good stable dispersion and what doesn't. So here, if it's not stable, all that work that you put into grinding the pigment, it all is for naught because they all come back into these big flux, if you will, and unstable. But if it's stabilized, it's going to take all that work that you put in there and it's going to maintain those small particle size for a very good dispersion, the highest strength that you can get in there to be able to do that. Rheology. Rheology is key into getting all of your the best that you can out of the pigment. So in a lot of cases, your pigment content is one of the largest cost items in your formulation. So of course you want to get the most out of your pigment that you can for your formulation. And what this information does is taking the same pigment, this pigment blue 15-2 alpha blue pigment, and we are comparing a number of polymers in the dispersant area and to look at the performance on the rheology of the system in here. So these are all formulated identically, the same amount of pigment, the same dispersion to pigment ratio in this area. So we're really just looking at the performance of the dispersant itself, the polymer choice itself, as it relates to this particular pigment. The other thing that I added to this study was to look at dispersants alone, as well as in combination with synergist in here. And the end result is, definitely the combination of the two is the best in terms of rheology, giving you the lowest dispersant or the lowest viscosity of that is available in here. So your choice that these are all part of the screening process when you're developing a formulation to be able to do that. So again, going back to that ultimate performance area, but it does tie into how the finishing choices for that product, how it relates to a formulation. Plastics, again, same idea here in terms of a dispersion. One of the key areas to evaluate how well a pigment disperses is to look at the filter pressure value, FPV, in here. So this is a series of a number of Pigment Blue 15-3s in the same plastic formulation. Each of these obviously are created for a specific end application area. So there's two from the plastic arena, two from the coatings, and three from classical ink, and two on the inkjet side in here. So you can see how there's a variety of results from a dispersion perspective, and that's truly due to just the choices of finishing techniques that are applied to that particular product. All the same chemistry, it's just that finishing choices that are used to get to that the end application area. So in short, it does offer some interesting results and options that you can consider as you're choosing a pigment to go forward with. You don't always have to stay basically stay in your lane. And if you're a plastic formulator, only select plastic grades in there. Others might work and might give you something that another will not. Stability. We talked about the individual dispersion stability, but also the stability of those dispersions when mixed into the final end product. This is an example. So these are the same formulation of color, same base in here, but the pigments themselves are the same. How they were dispersed is different. The formulation of the dispersion is different in here, and what we see is a variety of results in terms of settling and separation after 10 days of sitting in here. So depending on where you need to be, there what might be one choice is better than the other in terms of these types of properties. The photos that below indicate that there's definitely a difference in terms of how much settling is there, as well as the quality of the settling, whether it's soft settle, hard settle, and then the pictorials on the side just give you a feel for some of the measurements that we see in these formulations. Durability and functional performance. These are other characteristics of the pigments and the finishing, and how the finishing impacts these areas in here. So some examples of that are to follow here. Going back to that mica that we talked about earlier, here we're taking a look at the color retention of these same micas. And again, we see a difference in the choice of chemistry on the surface, as well as the amount of that chemistry. And ultimately, in the series of 6 examples, there is only one really that falls into that specification that the ALMA 2604 and 2605 creates for the delta E of less than 5 in there. Plastics, heat stability. Typically, the majority of the heat stability is dictated by the chemistry. There's no doubt about that. However, in some areas, the performance can be altered based on the choice of the finishing. The examples that I have here, Violet 19. This is the gamma version of Violet 19. We start to see one of the coatings grades as well as one of the ink grades. The heat stability does fall off a bit, still very good, but we start to see some fall off in the heat stability. Red 122. There's an example of both of the plastics, coatings, and inks grade. Here we also see some fall off, but in particular we see a lot more fall off, kind of equating to what a classical pigment will provide in terms of heat stability, because of the choices of the finishing used on that coatings grade Red 122. It really does detract the heat stability for that particular product. And then on the classical side, although classical pigment azo pigments tend to always have lower heat stability, we start to see some fall off of the heat stability by the choice of finishing techniques in that color index as well. Anti-corrosion pigments. There are ways that the finishing moves the performance based on that one. And so in this example, we are modifying a zinc with the orthophosphates versus the regular zinc phosphate in here to be able to get improved properties. So, as you know, I'm a very visual person here, so I go right to the pictures to give that example. So we have from the traditional zinc phosphate, we can move the performance in the crosshatch with the ZPO with this particular organic or orgophosphate treatment, and then even further in both the crosshatch performance as well as the scribe performance with this particular product in there. All surface treatments of the base zinc phosphate. In ink, UV ink, the particle size will also dictate the transparency, as we talked about before in other application areas. So in this example, there's several pigment yellow 13s that we evaluated in a UV offset ink formulation. And as you would expect, the most transparent version does have the most strength, but it also brings with it a very high yield value in terms of its rheology. The opaque, less strength, less impact on the yield value. But with finishing comes, as we talking about all the way through this presentation, is there's choices in terms of what we use. So the three on the right hand side, these are all to the opaque side, but the choice of finishing, and in this case, it's more the chemical finishing, also impacts some of the rheology in there. So depending on where it's being used, there might be a better choice in here. That's why looking at your choices and how you can fit the property to your benefit is where it becomes important. Plastics, the bleeding in the different polymers. So here we're looking at two violet 23s, but in different plastic application areas. The first one being in LDPE. Both of them are performing the same. When we switch that over to PVC, we start to see a bigger difference between the two. Again, it's that the choice of finishing on the pigment and how it interacts with the polymer that it's going into. So a few more examples, and then we'll wrap it up. Going back to that Pigment Blue 15-2 example, here we're looking at one pigment. So all of these are done via that drying process too, but we're looking at that pigment in three different types of formulations. Two polyurethanes, one on the water side and one on the solvent side, and one industrial alkylamine type systems. So again, we see a color development difference between the two. In the polyurethane formulations, we develop more red than the alkylamine, but the alkylamine develops more strength in there. So these are all of the scenarios to take into account when you're developing your formulation. If we look over to Pigment Green 7 in water-based ink, these are all a variety of finishing techniques on Green 7 and how it impacts both viscosity and gloss. So this is a nice scatter shot of a variety of options depending on how the pigment is finished. And then in plastics, there we talk about regular application and then fiber film as a separate sub application. Fiber film does require a more precise pigment in the end to be able to work well in those environments. So we test it differently. A smaller mesh size, as well as more pigment in there to be able to understand how well they are. And we adjust the finishing to meet these application areas. So the example here is a red 170 The regular grade, if you will, on that same 10 mesh screen has a very high filter pressure value, but the one that was created for a fiber or film application is low at 1.3 uh, FP bars per gram in there, and you can see how that relates to the surface area. So the finishing choices that we use for this particular product results in a smaller particle size, more surface area to be able to get to that better dispersion aspect of it. So we also see it in the film as well. So this is one that we always use, but it's a key one to be able to making sure that we understand it's always going to be a balance between the pigment and the application. And so why that I always stress that is key that we prioritize what is one of our musts, what is one of our, what we would like to have in our wants. And if we can get some of the nice to haves in our choice, that would be great too, but it is a balance, and there isn't a chemistry or a pigment out there that can give you everything that you're looking for in your formulation. So with this, I'd like